Actually, I just outside. And sure. No, for sure.
WhatsApp me and just come.
Vedo grosso, vedo dorato. Pensavo che per questi orari dovesse arrivare invece.
Good afternoon. Today we will cover we will review together some fundamental concepts of thermodynamics that we will use later on in the course. It's important to recall these concepts, and in particular how to describe vapor liquid equilibrium conditions, because we will use these equilibrium conditions to then model the unit operations we are going to study. Before going on, I would like to tell you that the exam rules are now available. I have published them on BIP in a separate file, so read them, and if you have any question either now or later on, of course, ask. And as you should know, today after class in this room, for those of you that cannot use Excel or whoever is interested in it, I will give an introduction to the use of Excel, so that if you want to use Excel to solve the exercise for the written part of the exam, you are able to do that. For this topic, considering the books I suggested you in the introductory class, the one you can refer to if you want to go deeper in some specific topics we will cover today is the second one, entitled The Separation Process Principles by Sitter. Sitter's the first author. Okay, so as I said, today we will cover the topic about phase equilibria. When we talk about phase equilibria, for example, vapor-liquid equilibrium conditions, we state that there exists a thermodynamic equilibrium between a vapor phase and a liquid phase. So it's important, before going on, to clarify what we mean by phase. A phase is any part of a system, any region, in which the intensive properties are everywhere the same. And when we use the expression intensive properties, we refer to those properties like temperature, pressure, and composition that do not depend on the size, the mass, and the shape of the system itself. So the phase is the region of the system which is characterized by this aspect, and which can be physically separated from the other phases, from which it is divided by means of a distinct interface. Okay? Now, if you think, for example, to this bottle of water, we know that inside this bottle we have a pure component, which is water, in a single phase, which is the liquid phase. And we have different variables that we can use to characterize this system, including temperature, pressure, entropy, enthalpy, Gibbs free energy, and many others. However, only some of these variables can be are independent on the others. Meaning that if we specify some variables, all the others can be calculated, can be determined in order to unambiguously describe the state of the system. And this concept is related to the degrees of freedom or variance of a system, which is the number of intensive variables that must be set in order to determine the state of the system. For a system in which we do not have any reaction, the Gibbs phase rule reported here allows us to determine the variance or the degrees of freedom of a system. This rule states that the degrees of freedom is given by C, which refers to the number of components in the system we want to describe, minus F, which is the number of phases that are present in our system, plus 2. We can better understand this Gibbs phase rule if we make an example, for example, considering pure water. So we are in the case in which C, the number of components, is equal to 1. And we can have different cases depending on the number of phases which are present in the system. We can also understand this if we look at the pressure-temperature diagram, which is reported for pure water here in this plot. So, as you should know, in this pressure-temperature diagram, we have some regions, the one which are of different colors, corresponding to a single phase region. So, for example, the light blue one is the one in which we have liquid water in the liquid phase. The green one is the one where we have the solid phase, so ice, and the pink one is the one where we have the vapor phase. These lines, so the green one, the blue one, and the red one, are the ones representing the equilibrium conditions in terms of pressure and temperature pairs between two different phases. In particular, the blue line that goes from the tripole point to the critical point of pure water gives us all the temperature and pressure pairs for which we can have the equilibrium between the vapor phase and the liquid phase. While as for the green line, this will give us all the equilibrium conditions between the solid phase and the liquid phase. And if we refer to this red line, it will give us the equilibrium conditions between the solid phase and the vapor phase. Okay? So all these lines are refer to the case in which two phases are simultaneously present within the system. So F is equal to 2. Now, if we consider the first case, in which we have a single phase, so F is equal to 1, we have that the degrees of freedom is given by, according to, we will apply the Gibbs phase rule, so it is given by 1, which is the number of components, so just pure water, minus 1 because F is equal to 1, plus 2. So it is equal to 2. And it means that we need to specify two variables, which are one independent of the other one, in order to unambiguously characterize the system state. For example, if we fix the pressure at 1 atmosphere, and if we are in the liquid phase region, we know that there exist different values for the temperature for which water can exist in the liquid phase among 0 and 100 degrees Celsius. So this means that if we fix the pressure, we also need to specify the temperature to characterize the state of the system. So the temperature is in this case independent of the pressure, and two intensive variables must be specified in order to characterize the system. On the contrary, if we consider the case in which F is equal to 2, so we have two phases simultaneously present in the system, according to the Gibbs phase rule, the variance is equal to 1, because we have 1 minus 2 phases plus 2 equal to 1. So this means that if we fix the pressure in this case, there exists only one value for the temperature at which we will have two phases, vapor and liquid, that coexist within our system, and this value is equal to 100 degrees Celsius. So in this case, the temperature cannot be fixed, specified independently of pressure, and this is why the degrees of freedom in this case is equal to 1. While when we consider the tripole point of pure water, or in general of every component, in which the number of phases is equal to 3, according to the Gibbs phase rule, the variance of the system is equal to 0. We have 1 minus 3 phases plus 2, so it's equal to 0. So we cannot specify any variable, in any intensive variable in this case, and this point, the tripole point, is indeed already given once we specify the pure component we are dealing with. So if we are talking about pure water, the tripole point conditions are known, are defined, and can be found on any handbook. These values are tabulated. Let's now focus on the vapor-liquid equilibrium conditions for two components. So if we move back to the Gibbs phase rule, we have that we have a binary system, so C is equal to 2. We have two phases simultaneously present, vapor and liquid, so F is equal to 2. So the variance of the system is equal to 2. This means that to define the state of the system, which is the equilibrium state between a vapor and a liquid phase, we need to specify the sign to intensive variables, choosing among the temperature, the pressure, and the composition of the vapor phase or of the liquid phase. We also should remember that according to the stoichiometric equations applied to the vapor and to the liquid phase, we have that the mole fraction of component 1 plus the mole fraction of component 2 in the vapor phase must be equal to 1, and this also holds for the liquid phase. So the mole fraction of component 1 plus that of component 2 in the liquid phase is equal to 1. However, as we said when solving the exercise last Thursday, when we deal with binary systems, typically we use only y and x, using no subscript, in order to refer to the molar fraction in the vapor phase when we use Y, and in the liquid phase when we use X, of the more volatile component. And as for the mole fraction of the less volatile component, we will denote it as 1 minus Y for the vapor phase and 1 minus X for the liquid phase, using these stoichiometric equations. Now, if we consider an ideal mixture, we know that in this case the Raoult's law applies. That tells us that the partial pressure of component, the generic component I, is equal to its vapor pressure, that is a function of temperature, multiplied by the molar fraction of component I in the liquid phase. So the first equation reported here. In addition to that, for an ideal mixture, we also know that the Dalton's law applies, which tells us that the total pressure of the system is given by the sum of the partial pressure of each component, which is given by the total pressure multiplied by the molar fraction of component I in the vapor phase. So if we combine these two laws, the Raoult's law and the Dalton's law, we can express the molar fraction of component I in the vapor phase as a function of the molar fraction of component I in the liquid phase. These two molar fractions are related by means of this ratio, which is given by the vapor pressure of component I at the system temperature divided by the system pressure. Now, if we define using K the equilibrium constant, which is defined as the ratio between the molar fraction of component I in the vapor phase and the molar fraction of the same component in the liquid phase, you can see that in this case, so in the case of ideal mixtures, this K, this ratio, is equal to this quantity here. So the ratio between the vapor pressure and the system pressure, which means that the K value, also called equilibrium constant, is a function of the temperature and the pressure of the system. Now, when do we deal with an ideal mixture? Typically, when we are working with mixtures that are made up of components with similar physical properties. We say we are dealing with homologous series. So, for example, this is the case of the binary system including benzene and toluene, which are both two aromatic components. Or the system which is made up of propane and butane, which are both two saturated hydrocarbons. Or the system that consists of methanol and ethanol, which are both alcohols. Okay? So in all these cases, when we have components with similar physical properties, we can treat the system as an ideal mixture, and we can express the vapor-liquid equilibrium conditions using these relations reported here. So as we said, in this case, the equilibrium constant, the K value, is only a function of temperature and pressure. When we deal with non-ideal mixtures, the expression of the equilibrium constant gets more complicated because it is not only a function of the temperature and the pressure of the system, but it also becomes a function of composition. When talking about the equilibrium conditions for between a vapor and a liquid phase for ideal mixture, we introduced the vapor pressure, which is denoted by PF. So as for the vapor pressure, we have different correlations that allows us to express, to calculate the vapor pressure of a pure component as a function of the temperature. In particular, we can discuss this dependence if we start with the Clapeyron equation that was proposed in 1834. If we consider for a pure fluid, for a pure component, the equilibrium equation, the equality with respect to the temperature. So we know that the temperature in the liquid phase must be equal to the temperature in the vapor phase to have equilibrium conditions with respect to energy transfer between the two phases. We also need to have that the pressure in the liquid phase must be equal to the pressure in the vapor phase. And in addition to that, in order to have equilibrium between the two phases with respect to mass transfer, we also have that the chemical potential of the component in the liquid phase must be equal to the chemical potential of that component in the vapor phase. And we will later better focus on this concept of the chemical potential. If we consider these conditions, which express the equilibrium conditions between the vapor and the liquid phase, it is possible by rearranging these equations and by using some thermodynamic relations, it is possible to end up with this equation reported here, which is the Clapeyron equation, that relates the change, the pressure to the temperature, that the change that we have in case of a phase and the equilibrium or the transformation from a vapor and a liquid phase using by means of this variable here that stands for the enthalpy variation that accompanies the transformation from the liquid to the vapor phase. So it's the difference between the enthalpy of the saturated liquid and the enthalpy of the saturated vapor. At the denominator we have the temperature and we have the difference, the variation in the molar volume that is involved in the transformation, in the phase change between the vapor and the liquid phase. So it's equal to the difference between the molar volume of the saturated vapor and that of the saturated liquid. So if we integrate this, the Clapeyron equation, we are able to get the dependence, to express the dependence of the pressure with respect to the temperature for a pure component. However, this requires to express this enthalpy variation and the molar volume variation as a function of the temperature and of the pressure, which may be complicated. So a simpler approach consists in solving that problem under some assumptions, which are the ones reported here. So first of all, we know that the molar volume of the saturated liquid is much lower than the molar volume of the saturated vapor. So in this expression, in the Clapeyron equation, we can neglect this term, the molar volume of the saturated liquid, and we can assume that this variation is equal to the molar volume of the saturated vapor. So we can then express this molar volume of the saturated vapor by means of the ideal gas law. So if you remember, according to the ideal gas law, we have that the molar volume is equal to the ideal gas constant times multiplied by the temperature and divided by the system pressure. And then we also assume the enthalpy variation to be constant and in particular independent of temperature in the temperature range of interest. So assuming all these, we can rearrange the Clapeyron equation in order to get the so-called Clausius-Clapeyron equation, which is the one reported here, that we can now integrate between a certain reference state indicated by the subscript ref and the system state, which is at a pressure T and at a temperature T and at a pressure P. Now, considering this dependence, you can see that we have, according to this equation, we have a linear dependence of the logarithm of the pressure with respect to the reverse of the temperature, 1/T. Okay, this relation is linear. So, based on these theoretical results, several correlations have been proposed in the literature. In particular, one of them, which is widely used, is the so-called Antoine equation. It is a semi-empiric modification of this equation because it's based, of course, on theory, but it makes use of some empiric coefficients, these three coefficients A, B, and C reported here, which are determined for each species, for each component, considering using experimental data, so measurements of vapor pressure as a function of the temperature. Consider that these three coefficients A, B, and C are tabulated, so they can be found in several handbooks in the scientific literature for a large number of components. They form a set, so you cannot take, for example, constant A from a tabulation and then the other constant B or C from other tabulation, but they form a set, so you should take them from the same reference, the same tabulation. And also, yes?
Like, why we are neglecting VL, vapor pressure of saturated liquid? The first assumption. The first assumption we are doing right. We are neglecting the vapor pressure of saturated liquid. Considering why we have to do.
No, we are not neglecting the vapor pressure of the liquid. What do you mean? Not the molar volume.
Why we are doing the first assumption?
This first assumption, because if you consider the gas and the liquid, if you look at the properties of the component in the gas and in the liquid phase, you can see that the molar volume in the liquid phase is much lower with respect to that in the vapor phase. This is also the reason why, for example, transportation of a certain substance is preferred in the liquid phase rather than in the vapor phase, because you can transport more quantity if you the same quantity in a lower volume if you transport it in the liquid phase rather than in the vapor phase. Okay?
Yeah.
It's an assumption that it's quite often made, and especially when you have to derive, you have to integrate and simplify these relations here, okay, for integration and to get this dependence. What I also wanted to point out is that typically the Antoine coefficients are given for a certain temperature range or in which they are valid. So it's important that you use them in that temperature range because extrapolation may lead to very strange and incorrect results. This is an example just to have an idea of where you can find these semi-empirical correlations and especially the coefficients you need to use to compute the vapor pressure. This book is The Properties of Gases and Liquids that was written by these three authors. And just to have an idea, in this book, three correlations are reported which allow you to calculate the vapor pressure of several species as a function of the temperature. Of course, in terms of different parameters that you can find that are tabulated in the same reference book. The first one is the Wagner equation. So we have the dependence of the vapor pressure with respect to the temperature given by this equation. In particular, in this case, this equation uses the reduced vapor pressure, which means the vapor pressure which is divided by the critical pressure of the component. When we use a reduced pressure or temperature, we mean that the pressure or the temperature is divided by the critical pressure, respectively, and temperature of the component. The second equation is of the type reported here. It's called Bartolot's equation. We have basically a polynomial function with respect to t in terms of different coefficients a, b, c, and d, which are also tabulated for the different species. And then we also find the Antoine equation that we mentioned before that expresses the dependence of the vapor pressure with respect to temperature in terms of the three parameters A, B, and C. Now we will use these concepts in order, so always dealing with a binary mixture, and in particular considering an ideal system, in order to derive the bubble point and the dew point equations that we will use, for example, in order to perform calculations for a distillation tower. So let's start from the bubble point equation. The first equation is the Raoult's law written for component 1. We have that its partial pressure is given by its vapor pressure multiplied by its molar fraction in the liquid phase. The partial pressure of component 2 is given by its vapor pressure multiplied by its molar fraction in the liquid phase, that we said is equal to 1 minus x. Okay, we use no subscript and we use x to refer to the more volatile component, 1 minus x to refer to the less volatile component. Then we know that the total pressure of the system P is equal to the summation of the partial pressures of the two components which are present in the system, so P1 and P2. that by using the Raoult's law, we can express as reported here. So as you can infer from this expression, you can see that if you plot the pressure with respect to x, so the molar fraction of the more volatile component in the liquid phase, you get a straight line which links the vapor pressure of the two pure components. So if you think of the pressure composition diagram of a binary ideal system, so we have the pressure reported on the y-axis. We have the composition of both the liquid and the vapor phases reported on the horizontal axis. We have that the bubble point curve is represented by a straight line. It should be a straight line. That for x equal to 0, so that means we have the less volatile component will intersect the y-axis for a value of the pressure which is the vapor pressure of component 2. While for x equal to 1, so it means that here we have the pure, more volatile component, we have that this point here corresponds to the vapor pressure of pure component 1. Of course, this plot is at a constant temperature. It is an isotherm diagram, okay? So every time you see the bubble point curve represented by a straight line in a pressure composition diagram, it means that you are assuming the binary system to have an ideal behavior. Now let's determine which is the equation for the dew point curve. In this case, we will write the equations as reported here, since when we want to get the equation for the dew point curve, it means that we have the vapor phase which is assigned, and we want to determine at which conditions the first drop of liquid will form within our system. So in this case, we will make use of the stoichiometric equation written for the liquid phase, which is the phase of which we do not know the composition. Okay? When we calculate the dew point of a certain system, we have the vapor phase and we want to know at which conditions the first drop of liquid will form. So by using again by combining the Raoult's and the Dalton's law for the two components, we can write that Y over the vapor pressure of component 1 is equal to X divided by the system pressure, because we said that by combining those two rules, the system pressure times the molar fraction of component I in the vapor phase is equal to the vapor pressure of component I at the system temperature times the molar fraction of component I in the liquid phase. So for component number 1, we can write this equation as reported here. And we can do the same for component number 2 using 1 minus y and 1 minus x for the molar fractions in the vapor and liquid phases. Now, if we use this stoichiometric equation for the liquid phase, we can we can combine these two equations as reported here. We can derive the expression for x and then sum and 1 minus x, and summing up the two expressions, we are left with this equation that we can rearrange as reported here on the right. This will give us an expression for the dew point pressure as a function of y, so of the composition of the vapor phase. As you can see from the form, mathematical form of this expression, this is not a straight line, it's a curve, and we can represent it on our pressure composition diagram as, for example, by drawing, for example, this curve. So the one we drew earlier represents the bubble point curve of our binary ideal system, while the one we have just drawn represents the dew point curve of our system. This is what is reported in the first plot, in the first graph here on the left. It is a pressure composition diagram where we have, we can better understand and discuss this diagram if, for example, you consider all the points which are reported here. Start, for example, from this point F, which is located here, so above the bubble point curve, in the region of the subcooled liquid, so where we have just one single phase, that is the liquid phase. We start with this point F here. So we have just the liquid phase of a certain composition that we can read on the x-axis. So here we have a mixture containing 40%, I think, of the more volatile component. Okay? So this point here is for a molar fraction of the more volatile component equal to 0.4. Imagine that you reduce the pressure of the system at constant temperature. So by reducing the pressure, you will reach at a certain point this value of the pressure, which is represented by point L here, where this is called the bubble point pressure of the system. At that point, you will have that the first bubble will form within your system. So you start with a liquid mixture, you decrease the pressure, at a certain point you will reach a value for the pressure at which the first bubble of vapor will form within your system. This pressure is the one that we can read, for example, on this pressure composition diagram. We can denote it using a P sub D, where D stands for dew point. And this bubble of vapor that will form is characterized by a different composition from the one of the liquid that we can read on the dew point curve, on the curve of the saturated vapor. So at this point we have a liquid that contains 40 mole% of the more volatile component, that is in equilibrium with a vapor, with the first bubble, that is characterized by this molar fraction of the more volatile component. The one indicated here by point V. If we further reduce the pressure, for example, if we stop at point M here, so let's assume this is point M, we are in the middle of this two-phase region. This is the vapor plus liquid equilibrium region. So it means that for each point within that region, we will not have a single phase, but we will always have, we will always have two phases simultaneously present within our system and characterized by different compositions. In particular, the liquid phase will have a composition that we can read on the bubble point curve, on the curve of the saturated liquid, the one denoted by M prime, I think. And the vapor phase is characterized by a composition that we can read on the dew point curve, on the curve of the saturated vapor, the one which is denoted by M second. If you further reduce the pressure, you will reach a certain point which is W, I think. Okay. So this point here, W, where all your liquid mixture has been vaporized, and you are left with just one drop, the last drop of liquid. This, the pressure corresponding to this condition is this was the bubble point pressure. This is the dew point pressure of the system, which is the pressure at which you have all your system in the vapor phase and just one drop of liquid within your system. So in this case, your vapor phase is characterized by 40 mol% of the more volatile component, while the liquid phase, the last drop of liquid which remains in your system, is characterized by a composition which is the one given by point Z, that we can read here on the x-axis. If we further reduce the pressure, also the last drop of liquid which was still present in our system will disappear, and we enter in this region, which is the one in which only a single vapor phase is present, which is the one of the so-called superheated vapor. Okay, is it clear? Okay, because this is also important when, for example, you have to design a certain process, or you need to choose the operating conditions of, for example, a separation unit. Of course, the operating conditions must be chosen in order to have the proper conditions. So if you want to separate the vapor from a liquid phase, the temperature and the pressure must be properly chosen. It makes no sense to operate the system at conditions where we have just a single phase, either a liquid or a vapor phase. We can also discuss that referring to the temperature composition diagram, which is the second diagram reported here. In this case, as you can notice, the shape of the lens is reversed because if on the x-axis we report the molar fraction of the more volatile component, when we have the pressure composition diagram, we have that the vapor pressure of the more volatile component is higher than the one of the less volatile component, while the opposite occurs for the temperature. So that's why on a temperature composition diagram, the vapor liquid equilibrium region is represented by a lens that has a shape like this one, where we have the single vapor phase at higher temperature, the single liquid phase at lower temperature, and this region represents the one in which we have the two phases, liquid and vapor phase, in equilibrium. So all the points which are reported in this second diagram have the same meaning as the same points that we discussed with reference to the pressure composition diagram. Everything is just reversed because if we consider the temperature, we know that the more volatile component is the one characterized at a fixed pressure, because that diagram is at a fixed pressure. It is characterized by a lower boiling temperature with respect to the less volatile component. Remember that for x equal to 0 we have the less volatile component, and for x equal to 1 we have the more volatile component. So lower boiling temperature and higher boiling temperature. So in this case, the point F we started here in the pressure composition diagram is located here at lower temperature, because here we have a subcooled liquid, and at constant pressure we need to increase the temperature in order to form the first bubble of vapor, and then we need to further increase the temperature to vaporize all the mixture until we reach the point W, in which we have the last drop of liquid, and we need to further increase the temperature to reach the region in which only the vapor phase is present. This behavior can be also reported, illustrated on a three-dimensional diagram in which we simultaneously report the pressure, the temperature, and the composition. So these are just particular cases of this more general diagram. Just notice that for x equal to 1 here, this curve linking the points U, B, and C, 1 is the one corresponding to the vapor pressure of the more volatile component, component 1, while this other curve from K to C1 is the one for the vapor pressure of component 2, which goes from this point K up to the critical point of component 2, while this C1 is the critical point of component 1. Okay, we can also discuss that in order to introduce another concept, which is the concept of relative volatility, by referring to a specific system, for example, the water methanol system. This plot here is not so nice if you look at it, but just because I took some experimental data of vapor-liquid equilibrium conditions, so they are characterized by some errors, that's why it's not perfectly shaped. The meaning of the plot on the left, which is a temperature composition diagram, is the one we have just discussed qualitatively in the previous slide. In this case, we have on the x-axis the molar fraction of methanol, because considering the binary system water-methanol, methanol is the less volatile, the more volatile component. Indeed, as you can see from this plot, at atmospheric pressure, because the pressure is fixed, it is characterized by a boiling point of about 65 degrees Celsius, while the one of water, as you know, is 100 degrees Celsius. So if you fix the temperature, you can relate, so for example, if you draw a horizontal line in this temperature composition diagram, you can relate the composition of the liquid phase, so X, to the composition of the vapor phase at different temperatures. These lines are called time lines. And you can plot these pairs, Y and X, as I did in this plot on the right, in which on the y-axis you have the molar fraction of methanol in the vapor phase, and on the x-axis you have the molar fraction of methanol in the liquid phase. The resulting curve is the one reported here, y as a function of x. It's this equilibrium curve reported here. In this diagram, I have also reported the y equal to x line, so the 45 diagonal, because by looking at the equilibrium curve which relates y and x, by looking at the distance between this equilibrium curve and the 45 diagonal, we can understand if the separation, for example, by distillation is easy or not. Because, of course, for the separation to occur, we must have a certain driving force. So the two phases must have a different composition. If they have the same composition, so if this equilibrium curve is very close to the 45 diagonal, so y is very similar to x, the driving force is very little, and the separation by distillation is very difficult. So maybe we may think to another unit operations to accomplish the desired separation. In this diagram, I have also reported for each pair the temperature as a function of x. To remember that each point on the equilibrium curve corresponds to a different temperature. As you can see here, each x-y pair corresponds to a specific different temperature, which is the equilibrium temperature of the system that is split into a liquid phase of a certain composition and a vapor phase of a certain composition. So this concept can be recalled here, in which the equilibrium curve for the system nitrogen-oxygen is illustrated. This is helpful, for example, when you consider the so-called ASU, the air separation unit. As you probably know, nitrogen and oxygen are separated by distillation in the air separation unit. So when dealing with this separation operation, you need to consider how easy is the separation between nitrogen and oxygen by means, for example, of distillation. And to do that, you can plot the equilibrium curve in the y-axis diagram. So here on the vertical axis we have the percentage of nitrogen in the vapor phase, and on the x-axis we have the percentage of nitrogen in the liquid phase. Because considering nitrogen and oxygen, nitrogen is the more volatile component. So as we anticipated, if this equilibrium curve is far from the 45 diagonal, then it means that the separation by distillation is easier. While if it moves towards the diagonal, which happens, for example, if we increase the pressure, then the separation becomes more difficult because the two phases will reach the same composition, so the driving force will decrease. The parameter that will tell us how easy is the separation, for example, by distillation, so the measure of this is the relative volatility that we typically denote using alpha, the symbol alpha, and is defined as the ratio between the distribution of the more volatile component between the vapor and the liquid phase with respect to the distribution between the same two phases of the less volatile component. So we have y over x, so the distribution of the more volatile component between the vapor and the liquid phase, divided by 1 minus y and divided by 1 minus x, which is the distribution between the vapor and the liquid phase for the less volatile component, characterized, as we said, by this molar fraction 1 minus y in the vapor phase and 1 minus x in the liquid phase. So you can rearrange this definition in order to get this expression of y as a function of x by means of the relative volatility alpha. If you plot this equation, you will obtain an equilibrium curve like the one reported in this plot here. So you can easily infer from this equation that when y is equal to x, so when the relative volatility is equal to 1, this separation is not possible because it means that our equilibrium curve will collapse on the 45 degrees diagonal, okay? So no driving force for the separation between the two phases to occur. So this separation is much easier as the relative volatility alpha exceeds unity, okay? So that's why the relative volatility can we take as a measure of the easiness or of the difficulty of the separation. I would like to go back just for a moment to the effect of the pressure illustrated here on the equilibrium curve. We said that by increasing the pressure, the equilibrium curve will collapse on the 45 diagonal and the separation gets more difficult. You can also understand that by looking at this temperature composition diagram in which the length is reported for different pressure values. You can see that by increasing the pressure, the vapor-liquid equilibrium region, so this the shape of that lens becomes stricter, meaning that the composition of the two phases get closer one to each other. Okay, so the same concept we already observed on the y-axis diagram. Just notice that this is a temperature composition diagram, which is different. It looks different from the temperature composition diagram we previously discussed. And this is why this occurs because on the y-axis, on the horizontal axis now, the mole fraction of oxygen, which is the less volatile component, is reported. So that's why the lens is reversed, because here you have the less volatile component characterized by the higher boiling point, while at 0% of oxygen you have pure nitrogen, which is the more volatile component characterized by the lower boiling point. If we consider ideal mixtures, we know you can, as you remember, you can relate the molar fraction in the vapor phase to the one in the liquid phase according to this expression. So using the vapor pressure at the system temperature and the system pressure P. These for the more volatile component and these for the less volatile component. So if you consider the definition of the relative volatility alpha, we said it is given by y over x divided by 1 minus y divided by 1 minus x. So according to this expression, y over x is equal to the vapor pressure of component 1 divided by the system pressure. If you consider the denominator of the relative volatility, 1 minus y divided by 1 minus x can be taken from this equation, and it is equal to the vapor pressure of component 2 at the system temperature divided by the system pressure. So by dividing the two quantities, the system pressure will cancel out, and you get this expression for the relative volatility between two components, 1 and 2, for an ideal system. So you can, in this case, you have that the relative volatility is given by the ratio between the vapor pressure of component 1 and the vapor pressure of component 2. As you can see, the relative volatility does not directly depend on the pressure. It is given by the ratio between two functions of the temperature. We know that, for example, using the Antoine equation, these vapor pressures are a function of the temperature. However, since it is given by the ratio of two functions of the temperature that have the same dependence on temperature, the dependence of the relative volatility on temperature is not that important, and it turns out that this relative volatility slightly depends on temperature. And this allows us to use an average relative volatility in our calculations. For example, when dealing, we will see that later on during this course, when dealing with distillation, this is the case where we will compute an average value for the relative volatility, and we will use it for all calculations. Here I have reported an example just to understand how, for example, just by knowing the Antoine equation, the Antoine parameters, coefficients of two components, we are able to plot, to build a pressure composition diagram at a fixed temperature for our binary system. So using the Raoult's law, which tells us that the partial pressure is equal to the vapor pressure times the molar fraction in the liquid phase, we can first compute the vapor pressure of component 1 at the system temperature, which was given and set equal to 75 degrees Celsius. So we have the Antoine equation or coefficients for component 1 reported here, the one for component 2. So first we can calculate at this temperature the vapor pressure of component 1 and the vapor pressure of component 2, which are the two values that we have here in this pressure composition diagram. Then we can obtain the total pressure by using the equation of the bubble point curve. If you remember, we derive it here. P is equal to this relation as a function of the molar fraction of the more volatile component in the binary system. So by using this equation, we have calculated the vapor pressure of the two components and the system temperature. So by assigning values to x, the molar fraction of the more volatile component in the liquid phase, in the range from 0 to 1, we can calculate the bubble point pressure of the system, and by plotting each pair pressure, liquid mole fraction of the more volatile component, we will have on this plot this straight line that, as we said, represent the bubble point curve for an ideal binary system. Then we can get the vapor composition by using, for example, this relation. So the Raoult's law written for component 1. That can be also rewritten in this way, that recalls us the equation we derived for the dew point pressure of the system. So once you calculate the molar fraction of the more volatile component in the vapor phase from this equation, you can now plot y, this y1 as a function of, or the pressure better, as a function of these values, y of the molar fractions of component 1 in the vapor phase, and by plotting these pairs, you will get the dew point curve of this binary system, this PY curve, which is the dew point curve that we discussed earlier. Okay, you want to have a break before going on? Okay, so let's have a 10-minute break.